We know that matter exists in 4 different states: 1 crystal, 2 liquid, 3 gas, and 4 plasma. Crystalline, liquid, and gaseous substances are abundant on our planet, but plasma is much less than these. This is why we know so little about plasma compared to others. It seems that plasma is not worth studying, or that plasma does not exist at all. But we are very wrong if we think like that. Although there is little plasma on our planet, there is a lot of it in the universe, that is, mainly stars. For example, 99.8% of the total mass of our solar system is the Sun, and the Sun is 100% plasma. The share of non-plasma substances by the total weight of the solar system is only 0.2%, that is, the amount of plasma is 500 times more than the crystalline, liquid gaseous substances in the solar system. This situation does not apply only to the solar system. This indicator applies to almost all parts of the universe, and of course black holes, pulsars and similar bodies with a very complex composition are excluded. Since the composition of the Sun is plasma, its condition is quite different from that of the planets. Because the planets are mainly divided into 2 types. 1 metal planets, in other words planets like Earth, Mars, and Venus. 2 gas planets are planets like Jupiter, Saturn, and Uranus. Planets are structurally simpler. Stars, in other words the Sun, are more complex in structure because they are plasma. Therefore, neither the atmosphere nor the inner layers of the Sun are similar to those of the planets. For example, we can say that the process in the core of the Sun is very different from the core of our planet. The composition of the core of our planet consists of heavy metals, the core of the Sun consists of gas. But since the weight of the Sun is 330,000 times heavier than our planet, the temperature of the core of the Sun is 3,000 times hotter than the temperature of the Earth's core, in other words 15 million degrees C. The radius of the Sun's core is 20% of the Sun's radius, so the diameter of the Sun's core is 280,000 kilometers. If we compare to this scale, the diameter of the Sun's core is 2 times larger than the diameter of Jupiter, but because the density of the Sun's core is very high, it weighs 350 times the weight of Jupiter. After all, the density of the solar core is 150 tons cubic meters. And the interesting part of this process is that the composition of the solar core does not consist of heavy metals like the composition of the core of our planet, but of the lightest gases, in other words hydrogen and helium. The very high pressure in the Sun's core is what causes the ultralight gases like hydrogen and helium to become so dense. The pressure in the core of the Sun is 26,500,000 gigapascals, which is 270 billion atmospheres of pressure. At the center of the Sun's core, 2,700,000,000,000 tons of weight are placed on a square centimeter of surface. If we imagine this very high pressure, it's like putting 250 liters of water in a 1-liter container, but this does not take into account the temperature of 15 million degrees C, and because of this very high temperature, the core of the Sun is the hottest point in the solar system. The Sun's core contains only 20% of the Sun's radius, yet the Sun's core makes up 34% of the Sun's mass. But the core has 0.8% of the total mass of the Sun. The percentage of hydrogen varies in the layers of the Sun. For example, if we look at the composition of the photosphere, the percentage of hydrogen is approximately 74%, and it consists mainly of helium. At the center of the Sun's core, the fraction of hydrogen is about 33%, and all but 2%, or 65%, is helium. The density of the Sun decreases with distance from the solar radius, that is, the density in the center of the solar core is 150 grams per cubic centimeter. And at a distance of 137,000 kilometers from the center of the core, that is, the density at the outer boundary of the core is 40 grams per cubic centimeter. This figure is 27% of the density in the center of the nucleus. If we move outward from the center of the Sun, the radiation layer begins after the end of the core. This radiation zone is about 300,000 kilometers thick and, like the core, it decreases in density as it moves away from the Sun's center. At the border of the radiation zone, with the nucleus, that is, the density of the inside of the nucleus is 20 grams per cubic centimeter, which is equal to the density of gold. And the density at the outer border of the radiation zone is 0.2 grams per cubic centimeter, which is 5 times lighter than the density of water. Similarly, the temperature decreases as you move away from the center of the Sun. The temperature at the boundary of the radiation zone with the core is 7 million degrees C, and the temperature at the outer boundary of the radiation zone is 2 million degrees C. The radiation zone is the transition zone between the core and the convective zone and extends 2/3 of the way from the center of the Sun to the surface of the Sun. Not all stars have a radiation zone. The main reason for this is the star's weight. If the star's mass is less than 0.3% of the Sun's mass, then the star will not have a radiation zone. As we continue moving outward from the Sun's center, after the end of the radiation zone, we encounter the tachocline layer, a thin layer that separates the radiation zone from the convective zone. After this layer, the convective zone begins. The thickness of the convective zone is about 200,000 kilometers. The convective zone is the outermost layer of the solar interior. The temperature at the base of the convective zone is 2 million degrees C and decreases as it rises outwards. The temperature at the outer boundary of the convective zone cooled to 5,500 degrees C. The heated plasma in the convective zone moves in a circle, that is, the plasma heated at 2 million degrees C at the bottom of the convective zone rises rapidly and expands and cools during its ascent. The cooled plasma becomes heavier and the heavy plasma begins to settle. During this circular motion, the plasma moves the hot temperature inside to the outside. The density at the bottom of the convective zone is about 0.1 grams per cubic centimeter, but at 200,000 kilometers above, that is, at the outer boundary of the convective zone, the density is 0.0000002 grams per cubic centimeter. This figure is equal to 1/10,000th of the air density at sea level. No matter how strange or incomprehensible the processes taking place inside the Sun and the processes taking place outside it may seem to us, these processes taking place in the Sun are completely consistent with the laws of nature.